This program is brought to you by the University of California, Davis on iTunes U. For more information, please visit us at itunes.ucdavis.edu.
Hello, third lecture. Welcome everyone. What will the journey be about tonight? Let me give a brief outline, okay, what it will be about, so on our little ideas board. So first I will go again briefly over this algorithm, right? The Castillo algorithm to evaluate for 0.5. How do you get a point on this curve? The other issue I will talk about is the issue of velocity vectors. I mean, there is a reason why this parameter is called t, right? The curve can be viewed as a piece of a line that is being curved. That's what it is. Take a piece of a line, a straight line segment, and you bend it, right? You deform it. That's what's going on. And the way it's deformed, that is given by the control points and the Bernstein basis functions, right? So, but if this is t and t for time, then you are traveling on this curve, right? That's the physical interpretation. And at each point, you also have a velocity, right? You move in a certain direction at a certain speed. So there is also this velocity vector I will talk about tonight, or the derivative, right? The derivative of a Bezier curve. And the other issue is related to splitting or subdividing. So if I have a very complicated curve, I would like to split it or subdivide it into multiple pieces or components. I would like to have a component here, one component there, one there, one there, one there, one there, one there, one there. So I have split this one curve into 1, 2, 3, 4, 5, 6, 7, 8 baby curves, mini curves, subcurves. Okay, how do I do that? Initially, I will start with a bunch of control points, and then how do I use the original sequence of control points to come up with control point sequences that only represent one of these pieces? Okay, so how do we do that? And once we know how to do that, subdividing a curve, then we also will use that concept to intersect curves, okay? So the next topic will be intersection, okay? I give you one curve, and I give you a second curve. And what we would like to find out is the location of the intersection. So these are the topics that I will be talking about tonight. So this fundamental algorithm that is used for evaluation is called the De Castillo algorithm. And all you really need to remember there is the geometry, the geometric construction, right? Because the arithmetic and the algebra follows from the geometry. Geometry. What are the ingredients for it? The ingredients are a control polygon, and the endpoints of this polygon are called circle, and then somewhere there is this parameter line t, and I designate a certain chunk of this line, typically 0 to 1, and deform it, and the deformation is entirely defined by this polygon. And what I need is points on the curve. So I say, I take this point, a particular value of t, so then this particular value of t subdivides this interval from 0 to 1 in a certain ratio, namely in the ratio t to 1 minus t. And the only thing one has to remember in this construction is that this ratio, t to 1 minus t, now gets repeatedly mapped onto all these line segments. So I take this ratio, this to that, and map it here, and map it there, and map it there. Okay, so all these splits are done in a ratio t to 1 minus t, t to 1 minus t, and t to 1 minus t. And then the intermediate points are used to connect to give me a new polygon, and I apply this ratio again. This ratio is mapped now here, t to 1 minus t, t to 1 minus t. And then I have one line segment left over, and again, I split it in the ratio t to 1 minus t, and the last point would be the point on the curve. And that is a particular point, curve, at the value of t. And if I were to draw an infinite number of points on that curve, I would get a picture like that. So you just slide this location between 0 and 1, and you get different points on that curve. That's the way it works. And this is all you need to really understand. From this, you get this double loop, the Casio algorithms that are put on the board, and this triangular scheme, all of that follows from just that construction. That's really all we need to digest and fully memorize. In fact, the only thing that you need to memorize is linear interpolation, right? Line segment, line segment. We just do the same thing over and over and over again. So we really only need linear interpolation. So that is it. The other thing is there is an important property of these Bezier curves. And so the important property is the convex hull property. Convex hull property. And someone remind me what that means? If I give you a polygon, then what can you state about the curve? The curve lies within the convex hull of the points that define the curve. So the convex hull of 3 points is the triangle that is spanned by these 3 points. So this is a convex hull. Okay. So the convex hull is a set of points, right? Namely, this all the points that make up the triangle. So the curve lies in that triangle, or is part of that triangle. So here is the curve. So if the curve is part of the triangle, then you can make it a little less severe, and you can say, well, if it lies in the triangle, it also lies in the so-called bounding box. Okay, and this bounding box is a very, standard concept in computer graphics. You compute the x-min, the x-max, the y-min, and the y-max for this window, and you can say that the curve lies in that sphere, or rectangle, right? If it lies in the triangle, it also lies in the bounding box that contains the triangle. So this is really the convex hull. This is the curve, and this is the bounding box. Bounding box. Okay. Why is this important? This is important when we go back later on to checking for intersections of curves. 2 curves can only intersect if their bounding boxes do intersect. If their bounding boxes do not intersect, curves cannot intersect. And based on that insight, you can write a very nice algorithm to find intersections. Okay? So we will come back to that later. So far, so good. This was our review. Are there any questions about this material? Is it all clear? Clear? Okay. Anything that I do not say or state in class, or that is not quite clearly stated, where do you find it? You find it in the book. By the way, everything that I say in class is in the book, right? Or the books. Right? I'm just the interpreter of the book for you, right? That's all I'm doing, right? I try to interpret the book for you. So the next important part of the lecture is concerned with derivatives, right? If I'm traveling on this Bezier curve, then I have a certain speed and I move in a certain direction. How do we compute that? Okay. What is the derivative of the derivative? Acceleration. You've taken physics, right? So there is the points on the curve. Then I have a velocity, direction and magnitude of that velocity vector. And then I have acceleration, okay, which will force me to curve around. So you have to compute derivatives in general. First, I just talk about the first derivative and then the general nth derivative. So derivatives of Bezier curves. Derivatives of Bezier curves. How do you get the derivative? By doing what operation? You derive, right? You differentiate. You differentiate. So we just use differentiation. All right. So the original definition, was a Bezier curve C of t is sum I from 0 to n bi times Bernstein polynomials bin of t. Okay, so now if you want to get the derivative of this thing, c, then we just differentiate with respect to t. That's all we do. So then the derivative is d dt of c of t. How do we get that? Well, we differentiate that sum. Right? That's what we do. Is this expression I from 0 to n bi bin of t prime. Okay. Now I give this to you as a homework assignment. You can do that at home to differentiate all of this. How do you do that? Well, you have to spell out what these Bernstein polynomials are, right? And I did this before, and you have to differentiate, right? And you use power rule, or that product rule for differentiation, and then you get it. So I just give you the result very shortly. So now you can put the differential operator in this sum. So it is bi times the Bernstein polynomials are the ones that you have to differentiate in the end. Bin of t, and you have to differentiate those. Okay, and then you have to spell them out, and then you apply all your rules for differentiation. And at the end of the day, after many, many steps, you get this. You get the differential is n times summation I from 0 to n minus 1 times bi plus 1 minus bi times bin minus 1 of t. Okay, so that is the derivative. Or in terms of physics, this is also denoted oftentimes as just c dot, right? You have seen that, c dot. What does this mean? Also, this is oftentimes written with a so-called differencing operator. So this difference here, bi plus 1 minus bi, is also abbreviated as follows. So this is n times sum from 0 to n minus 1 delta bi times bi n minus 1 of t. So this particular symbol there is called the forward difference operator, and it only is an abbreviation for this difference. So it is so-called forward difference operator. Right? So this meaning of it, delta bi, is simply bi plus 1 minus bi. Okay. Forward because you go one up in the index I, right? So when you apply this delta operator onto an index I, you add 1 to the index and then subtract the expression with index I. That's why it's called forward difference. Now we do an example, what this means. Example. And let me try to do a simple one. So a simple polygon, 4 control points. So this one would be B0, B1, B2, and B3. So n is 3 in this example. What do we need? What do we need? Take a look at this expression here. When you look at this expression, sum, something times something else, what does this look like? Does this look very different from the Bezier curve itself? Does it, or what has changed there? Not much, right? I still have a sum, except that the sum now runs to n minus 1 instead of n, so it goes down by 1, which is logical because if you differentiate a polynomial of degree n, it should go down to degree n minus 1, right? So that is logical. Here you have control points, right? Points, bi. What has happened here? Well, here you have differences of points. What is the difference of 2 points? It's a difference vector, right? So the point has become a vector, a control vector. And then these are these Bernstein polynomials, and here they are again, the same ones, except they are of degree n minus 1. They are the same, right? They're just 1 degree lower, because they have been differentiated, right? Obviously. But algebraically, these structures are the same. So we can probably also interpret this formula geometrically, right? This was a very formal derivation. Now we can go back to the geometry and try to understand what this means. So we no longer have control points, but we have control vectors for this derivative thing. Let's do it for this example. So what do we need? We need, here we have a curve. C of t is sum I from 0 to 3 times bi 3 of t. Okay. So I give these guys certain coordinates. So this is 0, 0. This is 0, 4. This point is 4, 4. And this point I want it to be 4, 0. Okay, so the derivative, so c dot of t is the derivative, is n times, so n is 3, so it is 3 times sum I from 0 to 2, these differences, bi plus 1 minus bi times bi 2 of t. Okay. So now I have to construct these control vectors from the control points. Okay. First I have to subtract b1 minus b0, then b2 minus b1, and then b3 minus b2. Where are these vectors? Well, they are these vectors, right? This is one. This guy is delta b0. This guy is delta b1. And this vector going down is vector delta b2. So how do I use something like a de Castelnau algorithm to construct the velocity vector at a point on the curve? Well, now these vectors become the control elements for our geometrical construction. Before we used points in our construction, now we use vectors. But you can also interpret vectors as being the positional vectors of points. So, and that gives you the concept of so-called hodograph curve. Okay. I take these vectors and draw them around the origin of a coordinate system. So I draw a coordinate system here, and I call it x and y. And I put these difference vectors somewhere. So the first vector, the first difference vector is this point minus that point. What is the vector then? b1 minus b0 is what? 0, 4 minus 0, 0 is 0, 4. So that vector, if this is the origin, here it is, right? Here is 0, 4. Right, so this is 4. The next difference vector is this vector. 4, 4 minus 0, 4. What is that? 4, 0. Where is 4, 0? 4, 0 is this vector from here to there. Okay, so this is 4. And this vector going down is obviously 4, 0 minus 4, 4, which is 0 minus 4. So that goes downwards, points from here to there. 0 minus 4, right? Minus 4. So now I have 3 vectors, but I interpret them now as points. So these vectors are just the positional vectors of these points. Bezier point, Bezier point, Bezier points. Okay? And now if I have 3 points, I can connect them as if they were to span a Bezier polygon. Okay, there's my polygon. And now I can evaluate the curve. Now I can also evaluate the curve. And I have a Bezier curve there. Right? But this curve is not to be interpreted as a curve, but it's to be interpreted as velocity vectors. How do I do that? Well, I can consider all these vectors that are starting from the origin and end up somewhere on that curve there. Okay, and all these vectors are velocity vectors of this curve. So here's a cubic curve, and if I want to get the velocity vector at the midpoint, say at t equals 1/2, t from 0 to 1, and I want to evaluate at 1/2, this is the point c at 1/2, and we know how to get the point. What we do not know yet is how to get the velocity vector there. Well, and here's the construction. I just evaluate this holograph curve for 1/2, and then I would get this particular point. Okay? This point is to be interpreted as a vector, which is a horizontal vector, which makes sense because that's a horizontal vector that is right there, right? The velocity. So this is the c dot at 1/2. So all these vectors that are defined by points on this curve, these vectors define the velocity behavior when I travel on that curve. Does it make sense? Well, initially, I'm going upward, right? Then I'm going horizontal to the right, and then finally I go downward, right? That's what I see here, right? I first go up, then I go horizontally, then I go down. That's what these vectors say. Okay. So if you were to evaluate a bunch of them, you would get the entire family of velocity vectors going up, staying straight, horizontal, and then going down. So this curve is 1 over n. There's this factor n there, right? 1 over n times c dot of t. And this particular vector here, this guy, would be 1 over, in this particular example, it's 1 over 3, it's 1/3 of the derivative at 1/2. All right. I want to give one other example of a Bezier curve. Why is it 1 over 3? Because there was the factor n in front of the sum. Remember I said the differential of the curve is n times sum. Okay, so it's that factor n. So I would not have to divide by n if I were to use the fact that 3 is part of the vectors and multiply all the vectors by 3. Okay, so 0, 12, 12, 0, and 0 minus 12. Then I get the direct velocity vector. I want to give you another example of an interesting curve. I want to give you such an example. Now that's a happy control polygon, right? It's zigzagging around. Here's one point, here's one point, here's one point, here's one point. What does the curve look like for such a thing? Okay, so this is my first point, B0. This is point B1. This is point B2. And here we have B3. Okay. Now, let's give these guys coordinates. So say this is point 0, 0. Let's say this point is 1, 1. So then this guy would be 0, 1. And this guy would be 1, 0. What does the curve look like? Huh? It does something, right? It does something. What does it do?
Would it loop at the top?
Hmm?
Would it loop at the top, like go like that?
Well, the polygon is looping, right? The polygon always resembles very closely the shape of the curve. That's why this Bezier scheme is so wonderful, right? Because the polygon implies the shape completely. Okay, so well, we would like to know what's going on there. We know that the first point and the last point, they coincide with the curve, right? But what's happening here? Is this looping or not? you can plot it, right? Plug it into your program and plot it and see what happens. Interesting thing is what happens at the midpoint, at t being 1/2. What happens there, right? It's somewhere there in the middle, right? So, okay, what do you get? You get c at 1/2. What is c at 1/2? C at 1/2 is probably 1/2, right? 1/2, 1/2. Maybe you get this point. Huh? If you believe me, you get the point 1/2, 3/4. Do it, okay? So if you do that, then you get by the construction, you will get the point 1/2 and 3/4. Okay, check it at home. So this point is the midpoint. Okay, and now you can plot it at home and see what happens. And I tell you, this is a curve. It's an interesting curve, right? It's a special case curve, but that's the way it looks. You start, you stop, you go down. If you think of it as a trajectory, right, then you're driving in your car, you drive up, you stop, you drive down. So this is very interesting because the velocity there is 0. So you start with a very high velocity vector in the beginning, and then your velocity becomes lower and lower until you really stop. And then you start over again, and the velocity is increasing as you go down. Such a point where your velocity is 0, and obviously these two tangent directions are different, discontinuous, is called a cusp. Okay? I'll give you a strange case here, but you should see it. So this is a so-called cusp. The interesting thing is that the velocity there is 0, but the second derivative is not 0, so then it's called a cusp. And the interesting thing, and c dot at 1/2 is 0, but the second derivative, which I haven't talked about yet, how to get it, second derivative at 1/2 is not is different from 0. So therefore, this is called a cusp, such a point. Any questions so far? Or is it all clear? Again, anything that is not quite clear during the class, when I talk about it, you can get complete clarity when you read the book. Right? How many books do you read typically per day? Technical books. I do not mean prose, but always have to read 2 or 3 newspapers per day, right? 1 book per day, 1 technical, 1 prose, and a novel. 10 journal papers to just stay up to date what's going on, right? Pardon? No, I have to do that. I have to do that. You have to do it too, right? So, if I can compute the first derivative, then I can also compute the next one. It's all the same, right? If I know how to take a curve and differentiate it once, I can continue to do that. It's all by induction, right? The same thing. So, how do we do that? Now we want the general formula for higher order derivatives, or higher degree derivatives, higher degree derivatives. Higher degree derivatives. So, again, the definition is a Bezier curve, C of t, is defined as sum I from 0 to n Bezier points bi times Bernstein polynomials bin of t. And now we differentiate it r times. So we want to get dr dtr c of t. And you have to differentiate these polynomials r times, and you get the following expression in the end. Again, you can do that either by hand, or you can use a symbolic solver like Mathematica or whatever you like, and you get it in closed form. So the closed form will be n factorial over n minus r factorial times summation sum I from 0 to n minus r. And now there will be this forward operator, again forward difference operator, delta, applied r times delta r of bi super n minus r of t. It might look ugly, but that's the way it is. And in a sense, it is the same creature that we start to begin with, right? We start with something where we have a sum points polynomial. We have the same thing here. Sum vectors polynomials. It's the same thing. We only have to understand what are these guys, right? What are these forward differences? Forward differences. Of original control points, of control points. And I'll just do some examples what these delta R creatures are. Okay. Let's call it remark. So what is delta applied 0 times to a control point bi? If I apply the delta operator 0 times, then, well, I get the point itself. So this is bi. Okay. Then we had this before. Delta applied once to bi means that I increase the index by 1 and then subtract the expression itself. So this is bi plus 1 minus bi. What does it mean to square this operator or apply it twice? So delta square bi. Well, that means that I apply it twice. That means delta of delta. That means I apply the delta operator to delta of bi. Okay, what does it mean? I apply it twice. So delta of delta. So that is the delta operator, difference operator applied to bi plus 1 minus bi. Okay. And now I apply this operator that acts on the index again. So that means I move the index up by 1 and then subtract the argument. So it is bi plus 2 minus bi plus 1 minus bi plus 1 minus minus bi, so that is plus bi, which is bi plus 2 minus 2 bi plus 1 plus bi. Okay, so I only do that in this case, that I actually do it by hand. And now, what happens when I do this 3 times, delta 3 of bi, and I just give you the result. Why do I have the result memorized in my head? Well, I have not memorized it, but I see the pattern. Okay, so this one will be 1 times bi plus 3 minus 3 times bi plus 2 plus 3 times bi plus 1 minus bi. Okay. And when you look closely, you already see the pattern again. Here the number is 1, here it is 1, here it is minus 1, and here it was 1 minus 2, 1, right? 1 minus 2, 1. And here we have 1 minus 3 plus 3 minus 1. And you remember that there's a pattern there, right? This has to do with these numbers appearing in the Pascal's triangle. That's how I can remember it. So again, these numbers here, this one, and this minus 1, and this one, this minus 2, this plus 1, and then here we have a 1, a minus 3, a plus 3, and a minus 1. These are the elements of Pascal's triangle with alternating signs, right? Plus, minus, plus, minus, plus, minus. So the coefficients of delta R bi terms come from Pascal's triangle. Pascal's triangle. Okay, so if I draw it, the Pascal triangle looks like this: 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. And then I said, now the sign is alternating, so it is plus, plus, minus, plus, minus, plus, plus, minus, plus, minus. Right, and these numbers you see in front of these expressions. Now the interesting part is that all the derivatives of a Bezier curve come out as a byproduct when you actually evaluate the curve. That is the beauty of this triangular scheme. I had a scheme there, which was a triangular scheme, right? That scheme contains all the derivatives. Again, the derivation to do that in detail is in the book. So I give you the answer. You do not have to use a particular formula that I have on the board to compute the derivative. You can do it much more simply. Namely, you only have to use the numbers you already have as part of your de Castillo algorithm. That algorithm gives you everything, not only the point on the curve. As a byproduct, it gives you the velocity, the acceleration, the third derivative, everything, all the derivatives. Okay. All right. So there is a theorem or lemma, Seebeck, Ferencz book. The derivative, the art derivative dr dtr of c of t is also given by the following expression: n factorial over n minus r factorial times delta b0 n minus r. And that's it. And these things are elements in the de Castillo scheme. Very hard to see, so I do an example for n equals 3 for a cubic curve, so you know what this means. Whenever I do not understand a particular formula myself, I draw either a picture or I have to write it down for a low number and actually see the pattern, or I understand it. So what does this mean? I do an example for n equals 3. Example n equals 3. What is going on? I would like to compute a point on the curve, i.e. the zeroth derivative, a velocity, first derivative, and an acceleration, second derivative. So a point would be the zeroth derivative. That means r is 0. Okay, so there's just the point. That means c of t is 3 factorial over n minus 0, 3 factorial, that is 1, delta r, I forgot the r forward difference of b0 n minus r. What is r? R is 0. 0 n minus 0, that is 3 minus 0, b0, 3. is B03. Okay, that is an entry in this triangular scheme. We come back to that. So what is this first derivative? R is 1, the first derivative, right? The first derivative, C dot of t, is what? Now I plug, which numbers do I use? N is 3 and R is 1. Okay, in this example. N is 3, R is 1. What do I get? So I get 3 factorial over 3 minus 1 is 2 factorial. So 3 factorial over 2 factorial is just 3. Huh? So that would be 3 times what? R is 1, so it's delta 1, delta operator applied once, delta applied to 3 times delta applied to B0, 3 minus 1 is 2. Delta B0, 2. Okay, and the delta operates on the lower index, so this would be 3 times B1, 2 minus B0, 2. Okay, so that is the first derivative. Okay, so now I also do it for the second derivative, and then I make the picture. And the picture we can memorize easily. So now I compute the acceleration of such a curve. C dot dot, second derivative of t is what? So now we have to say n is 3, and the derivative r is 2, right? Second derivative. What does it mean? So it is 3 factorial over 3 minus 2, that is 1. 3 factorial over 1 factorial, that is 3 times 2. So it is 3 times 2 times the delta operator applied twice, delta 2 applied to B0. B0, 3 minus 2 is 1. Okay, now I spell this out. And so this would be 3 times 2 times what? Delta applied twice to the lower index. So this is B2, 1 minus 2, B1, 1 plus B0, 1. Okay. All right. And now it's time to make a picture what that means, or where these numbers are. I said all these numbers come out of the triangular scheme. So insight, this is a fundamental insight. All derivatives are a byproduct of the triangular de Castelnau scheme. Okay. For n equals 3, our particular example, we remember the scheme looked like this, right? There was a B0, a B1, a B2, and a B3. Okay, and these are the original points, so they had a superscript of 0 because they are of generation 0. They are the original ones. And then from that we computed the next generation points, and we called those B, B, B. And again we start indexing at 0, 0.0, 0.1, 0.2, and they are of generation 1. So their superscript is 1, 1, 1. These we use to construct the points of the next generation, B0, 2, and B1, 2. And then finally, we get a point on the curve, which was B0, 3. Now, all these numbers these you compute to get the point on the curve. And I said all the derivatives are in that scheme. Where are they? Okay, here, this number here is the point on the curve, right? The curve point is B03. Where is it? Where the curve point is right there at the very end of the scheme. This is the B03 thing, right? That's the point. Now, where's the derivative in the scheme? Where is the derivative? The derivative is related to these numbers, B12, B02. Where are they in the scheme? Do you see them? B12, B02. Here, right? So this column contains the relevant numbers you need for the derivative, right? You compute the difference of these two numbers, and then you multiply by this factor of 3, and you have the derivative at that point. Okay. Now, what about the second derivative here, c dot dot? C dot dot depends on 3 values, these, B21, B11, B01. Where are they in the scheme? They are here, B01, B11, B21. So you have computed all these numbers, they are here in the scheme. Okay. Now you only have to multiply them by certain values, etc., to get the derivatives, but you have the numbers. All the numbers are here, which is very cool. That means you do this scheme once and you know everything that you want to know about the curve. Points, derivative, acceleration. It all comes out as a byproduct. Very nice. So here, I just put the factors there that you have to multiply it with. Right? So you have to multiply this guy by 1 times 1, and the other one, this was times 1, and this one was times minus 1. And then here you have the next one. This was times 1, and then the next number was times minus 2, and this one was times 1. Right? And those numbers, these guys, those numbers are the numbers that you see here. Right? Here is a 1, here is a 1, here is a 1, minus 1, here is a 1, here is a minus 2, there is a plus 1. Okay? So those numbers you have to use to multiply the entries in this column. But that's just a multiplication. This is very cool. That is how to differentiate a Bezier curve. Now, the next important topic is related to your first assignment, I believe, subdivision and intersections of Bezier curves. So again, what is the main idea that we want to study? Now comes subdivision. Subdivision. The idea is very simple. I give you a Bezier curve, which is too complicated for me to handle in some sense, so therefore I want to represent it by a bunch of chunks which are easier to handle. Okay, so one Bezier curve from here to here, and I subdivide it into multiple chunks, maybe 4 chunks, maybe 8 chunks. Okay, and the question is, if my original control polygon looked somewhat like that, with these points, and this being the curve, how do I get the individual chunks, and how can I represent them, each one in their own right, as a little Bezier curve? Right? Because obviously, I want to preserve the overall shape. The curve remains the same. It is just that I take the entire curve and represent it by 8 chunks instead of 1. So each chunk still has to be of n equals 3 of cubic degree, right? So where do I get these guys? How do I get these control points for the individual chunks? How do I get the 3 control points for this chunk? Right? So that is the principle of subdivision. I have one control polygon, one huge curve. I want to represent it by a bunch of smaller curves. And then the question that arises is, how do I get the control polygons for the smaller chunks? And again, it seems that this Descartes' algorithm and this triangular scheme and so forth is universal and does it all for us, right? Again, it turns out that by performing this algorithm, the Descartes' algorithm, you get the control points for each of these little pieces automatically as a byproduct. Isn't that nice? Is it? It is. It is nice. Right? So, how do I get them? Let's speculate. Do not copy this. This is just kind of like to make a picture. Whenever you want to develop an intuition for something, you start with a picture, right? And then the picture lends you to the path of success and seeing the general principle, right? So don't copy this. This is just helping us to find, to get enlightened. So I give you a quadratic curve, 3 points. And when I do this Descartes' algorithm, what do I have to do? Don't copy this yet. Point 1, point 2, point 3. When I evaluate this for the midpoint for 1/2, right? 0, 1, and 1/2. When I evaluate it for the midpoint, I take the midpoint, I take the midpoint, I connect, I take the midpoint. That's it. And the curve that I have is ha. The curve consists of 2 chunks. The overall curve was given by 3 circles, but now chunk left and chunk right are also given in their own right by 3 control points each. This control point, this control point, that control point. Looks like this polygon is the control polygon for that, right? Isn't that nice? And this guy, that point, and that point span the control polygon for chunk right. So we started with 1 curve from here to there, and we somehow see how the big polygon becomes 2 smaller polygons defining a left chunk from here to there and the right chunk from there to the very end. Now that's cool. No? Why is that cool? Now if you understand this principle, you can iterate it, right? If you can take 1 curve and create 2 from it, then you can take the 2 and generate how many from it? 4, for example. 8, 16, and so forth, right? So you can iterate this. What did I do? What did I do here to get the control? Well, it turns out you speculate or you follow your intuition. You say, well, Bernd, you just evaluated this curve and you got these intermediate points, right? These, and it looks like these points are the control points for the individual chunks. And then you have to formally prove that, and yes, it's true. All these points that come out as byproducts of doing that scheme are the control points of the individual chunks. Okay. Now that's the intuition. You have to look at the book to see the proof that that intuition is true, and then we can write it down, how to find the points. Shoot.
Why would you want to subdivide it?
Why do you want to subdivide it? Why do you want to subdivide it? Right now I talk about subdivision. At the beginning of class I said the ultimate goal, where I would like to steer the lecture at today, is the goal of intersection. Why do I want to subdivide? Why is subdivision relevant for intersection?
The entire curve.
That's it. Okay? So he's already thinking ahead. So right now I just talk about the building block. This building, don't copy this. This is just going back to your remark and question. Why do I do that? Because I want to solve this problem. I have a very complicated curve, and I have another complicated curve. Right? And I want to find out where these curves intersect. And solving that problem for the original complicated curves is difficult. Therefore, I take these complicated curves and make them simpler. Simpler in what way? Simpler in the way that I take the first curve and represent it by a bunch of smaller pieces. Okay? Take the second curve from here to here and represent it by a bunch of simpler pieces. Okay? Okay, now the question then becomes, okay, now you have all these smaller curves, shorter curves, and you ask, does this curve segment, now we are talking about individual segments of the curve, does this segment intersect with that one? Does it? No. Okay. Does this segment intersect with any segment there of this curve? No. By making it smaller and smaller, making these segments smaller and smaller, what do? You reduce the space where the curves actually do intersect. And you see that, well, the intersection has to happen here, right, in that region. Right? The intersection is happening here. And ultimately, you want to make the segments so small that they are pixel size. Pixel size, right? And you don't need to resolve it below pixel size. Or millimeter, or nanometer, whatever you have. Here is the intersection, right? That's what you get. That's why we subdivide. All right. That was looking ahead. So here we have this wonderful intuition. Subdivision. Subdivision. Okay. And I just stated the upper and lower entries in the triangular de Castillo scheme are the control points for the two segments of a Bezier curve. The upper and lower entries in the de Castillo triangular scheme are the control points for the two segments of the curve, are the control points for the two curve segments. Two segments. Meaning what? We breathe meaning into those words by making a picture and drawing the scheme. All right. So, picture and scheme. So on the left I put the geometry, geo, and on the right I put the scheme. So what should I do? I use a simple cubic, all right. 4 points, B0, B1, B2, B3. So the scheme then is B0, B1, B2, B3. And now I just fill out the entire scheme. So this is B0, B1, B2. And these two guys and these two guys combined, B0, B1, and the last one is B0. Okay, now comes the generation or column index. This is generation 0. This is 1. And here we have 2. And here it's 3. Okay. All right. So I say I want to split the curve at a particular value for t. The curve is assumed to be defined over the interval 0 to 1. And I want to split it at, say, this particular value. And I call this value c, okay? I want to split at c, and splitting at c means I just evaluate for c. So when I map this ratio, here I get this point, I get this point, I get that point, and I connect. I use the same ratio again, get this point and get that point, I connect, and I get the eventual point on the curve, that point. The whole thing has to be a cubic curve, right? Obviously, here is the cubic curve. But now you already see that this curve consists of two pieces, namely the piece from the evaluation point to the beginning and from the evaluation point to the right end. The original curve was defined in terms of 4 circles, and now each of the pieces are also defined in terms of 4 control points. Where are they? Well, obviously this guy here this segment, follow your intuition, this segment is defined by a circle, this point, and the point on the curve. And the right segment, this segment, is defined by a point on the curve, plus this and this intermediate point and the last point. Right? Comes out as a byproduct. Now, so we put the names here. So this is B00, 0, this is B10, 0, this is B20, 0, and this is B30, 0. Now the intermediate points, this is called B01, this is B11, this is B21, and then this point is B02, this point is B12, so the point on the curve, this guy is B03. So that means that this point, that point, that point, that point are the control points for the left chunk. Where are they in the scheme, in this scheme? It's B00, B01, B02, B03. 00, 01, 02, 03. All the ones where the lower index is 0, these guys, right? These guys. These guys are the control points for the left chunk. Again, they are byproduct, right? They come out of the scheme. Isn't it wonderful? So the other thing is, where are the control points for the other, for the right segment? So this is B03, 12, 21, 30. Where are they in the scheme? 03, 12, 21, 30. They are here. 03, 12, 21, 3, right? You go backward. Here. Here are the other. So this is a 3. The other control points are living here in the lower row. That's why I say the control points for the left chunk and the right chunk are in the upper row, right? That's the diagonal, and in the lower row. It's wonderful. So this is the control point information for the curve on the left. I call it CL. And this is the control point information for the curve on the right. I call it C on the right, CR. Right, so what did I do? I took the curve and I split it into left chunk, C left, and into right chunk, C right. Right? Very nice. Geometry in the scheme. And I get the definition, the control point information for both chunks by just performing the De-Castelnuov algorithm once. So now that we have that, this was the geometry and the scheme. Now we can also write down the equations for CL and CR. Right? So we had, or algebraically, we started with a curve C. C of t was the curve sum I from 0 to arbitrary n, right? Arbitrary n. And I have the original points, bi times bin of t, and t ran between 0 and 1. Now what I do, now I take the curve and split it into a left curve and the right curve. So after subdivision, division at t value c, I get two chunks, namely the left chunk, the curve on the left, CL of t, is what? Is sum I from 0 to n. And the left chunk is defined by the upper row, so it is the B0 super i's, right? B0 super I. B0 super I times bin of, and now I have to normalize this because the argument always has to be between 0 and 1. So it is t over c. For the first chunk, for t running t element, t in 0 to c, right? 0 to c is the first chunk. And the other part is the right component, c right of t, is sum I from 0 to n. And now I have to find the formula for these Bezier points on the bottom. So that is always the lower index starts at 0, 1, 2, and goes up to n. And the upper index starts at n, 3, and then goes down to 0. So it's b sub I super n minus I times bi n of, and now I have to normalize by 1 minus c, divided by 1 minus c, and it's t minus c. This is for the other part, where t runs between c and 1. This is just a formal way of expressing what the new control points are for the individual pieces. So one curve has become a left and a right curve. All right, and now comes the reason why we're actually doing that. Why do we worry about subdivision? And one main reason is intersection. Why? Why do I do that? I do it for a purpose, and now comes the purpose. The purpose is intersection computation. By the way, I could do the class in a completely different way. I could start the class and say, let's build a computer-aided design system. Okay, and I ask you, what do you want to do with the computer-aided design system? And you say, I want to generate a bunch of surfaces that look like the creatures in Bug's Life, right? And then I ask you, okay, you guys get together and you worry about all the functionality that you would like to have in a computer system that allows you to generate all the trees, all the plants, all the bushes, all the landscapes, all the creatures in Bug's Life. And once you start talking about it, then you worry about, I need 2 points, I need line segments, I need curved surfaces, I need a bunch of operations for these curves and surfaces, right? And then comes texturing and lighting on top of all of that. That's one way how I could teach the class, right? I start with the big purpose, namely generate a computer-animated movie, and then you will see that you need a bunch of building blocks, right, modules to do it, to make it happen. I do it the other way here. I start giving you all the building blocks, and at the very end, you have to see how these building blocks can be used to write a system that allows you to do computer animation, right? There's pros and cons for either way. But right now, I'm just giving you all these little building blocks. In the end, you have to see how it all fits together. And so the advanced geometric modeling course is about, okay, now I have all these modules, these 117 functions for curves and surfaces. Now I actually want to put them to good use, right? For modeling a car, an aircraft, a ship, or do computer animation, right? So, and you should see how all these things relate when we come closer to the end of the class. Intersections. Why? For computing intersections. For computing intersections. Intersections. Okay. We take advantage of 2 facts. First, the property of a Bezier curve that it lies within its bounding box of its control polygon. And we take advantage of this property, how we subdivide a curve into 2 pieces. Okay. So, first, 2 Bezier curves cannot intersect if what? A Bezier curve always lies in the bounding box of its control polygon. So therefore, 2 Bezier curves can never intersect if this. If I give you a first curve defined by this polygon, and this polygon has a certain bounding box, and the curve is this. If this bounding box, this BB, I call it BB1, bounding box 1, that contains curve number 1, does not intersect with bounding box 2 of the second curve, here, this guy. Here's the curve, here's its bounding box of its control polygon. This is BB2, and here's curve 2. BB1, BB2 do not intersect, so therefore the curves cannot intersect. That's good. No? So you say BB1 intersection with BB2 is 0, right? Empty set. Then curves do not intersect. Therefore, C1 and C2 do not intersect. Cannot intersect. Cannot intersect. Okay, good. What is case number 2? Case number 2 is bounding boxes do intersect. What can you say then? If the two bounding boxes of two Bezier curves, the control polygons, do intersect, then what? Curves do intersect or do not? Might. That's the point. They might or maybe they don't. Okay. So BB1 intersection with BB2 is not empty, then case A or case B or B. Okay. Let's draw a case where they do not intersect. So I give you a polygon here. First polygon. Here's its bounding box. And second polygon would be here. Okay. Here's the bounding box for that guy. And the curve is here. Okay, so the two bounding boxes do intersect in this little region, but the curves don't intersect. Okay, so BB1 is here, BB2 is here, but the curves do not intersect. The other case is bounding boxes intersect and the curves intersect. So, easy case, draw a polygon and a curve, bounding box. Okay, and second polygon here. Okay, which has this bounding box. Okay, and there is actually an intersection point right there. What we are after is the intersection point. Or first a decision, they do intersect, right? First we would like to know the fact that they do intersect. How do we do that? This is all that you need to understand in terms of writing an algorithm. These principles or these facts are all you need to write an algorithm to compute intersections. How? Why? Why is it enough?
If any of those bounding boxes intersect, and if they do, you test it for those and do the same thing. You just iterate down until you have two really small bounding boxes, and once you have pixel-sized bounding boxes, if those intersect, then that's what the intersection is.
Do you get that?
Yes.
His reasoning? What is your name again?
Garrett.
Garrett.
Yeah. That's it.
Garrett.
Yeah.
So, one more time. He says, and this intuition is good, I take advantage of the convex hull property or bounding box property. A Bezier curve is a subset of its bounding box. And when two bounding boxes do not intersect, the two curves don't intersect. When the two bounding boxes do intersect, the curves the curves could, but do not necessarily have to intersect. How do I find out? Now we go back to this other building block, curve subdivision, right? When checking two curves directly is this case, I cannot resolve it. then I split the curves. So I want to check two curves for intersection. I take the first curve and split it into CL and CR, left and right curve. And I take the other curve, the second curve, and split it into CL and CR, left and right curve. And then I compare the two child curves against each other. Until I have subdivided the curves down to the level of a pixel, and I no longer care. Okay, if the bounding boxes of a particular segment are of pixel size, then I say they do intersect in that pixel. So you have that's the termination criterion. You just stop there. You still haven't resolved it analytically, but you just say that's good enough. They are within pixel distance. Okay. So let me just put this on the board again, and then I will continue right at that point next time. So therefore, algorithm split two Bezier curves over and over again, and check whether the much smaller curve segments do intersect or not. Curve segments do intersect. So for the very simple case of just checking two lines, whether they do intersect or not, that's what I can draw. Example, two lines, right? A line is just a special Bezier curve where I just have two control points, B0, B1. The line is a curve, right? So I have a Bezier curve defined by this polygon. If I just have B0, B1, well, this is my bounding box, and the curve is the line. So here is this thing. Now, if I recursively subdivide a line segment, what are the bounding boxes of its children? So the bounding box for this guy is this rectangle. If I recursively subdivide this line segment always at the midpoint, then you will believe me intuitively that if I split it into the left and the right chunk, I get two same length line segments, and their bounding boxes will look like this. So this is the bounding box for the left chunk, and this will be the bounding box for the right chunk. Okay, if I repeat this again, I take these child line segments and I split them again, split here and split there, then the bounding boxes shrink. So the bounding boxes now for these four child segments become these guys. Here's a bounding box, here's a bounding box, here's a bounding box, and here's a bounding box. Okay, and I can iterate that. They get smaller and smaller. And now I want to check whether this line, this is the second curve. This was the first curve, right? In its entirety. Here's the second curve, and here is its bounding box. What have I done now? The question was, does this curve, curve number 2, intersect with curve number 1? And I wasn't able to decide because the bounding boxes initially overlapped, right? They overlap. So I do not know. Do they intersect or they don't? So therefore I say, if I cannot decide, I subdivide each curve. And in this case, I only subdivided the first one. But in the algorithm, you would subdivide both at the same time. And then in the next step, you already have resolved it. Because in the next step, you have a left bounding box, this guy, and a right bounding box for this one. And these two boxes do not intersect any longer with the bounding box for the second curve. So therefore, you have resolved it. The lines cannot intersect, and you're done. Right? And the other case, and you can think about that at home, the other case is, of course, when you do have an intersection. Right? You want to get the intersection point. And in that case, you will be subdividing down to the size of a pixel, and you say that pixel is the location of intersection. That's it for tonight. Thank you.
The preceding program was brought to you by UC Davis on iTunes U. Please visit us at itunes.ucdavis.edu.